Hello, welcome to another video on my channel. Today we are going to be talking about zero-knowledge cryptography. Today this video is going to be slightly different than my other videos. Although I have some older videos where I do code and a live stream. Well, that's going to be sort of the vibe for this video. You know, if you're a subscriber returning to my channel, you're probably thinking, well, I subscribe to a guy who's talking about life in Russia. Well, this video is actually very related to why I like living in Russia. Sort of related. And although we're not going to be talking about politics, this video is quite political. So I got some house music. We're going to be vibing. At least I'm going to be vibing. I don't know about you, but I'm definitely vibing when I'm talking about zero-knowledge cryptography. And that's what we're going to be talking about today. So this video is political because people who designed programs and applications that used this technology, zero-knowledge cryptography, and allowed people to increase the privacy of their transactions or just their privacy on the blockchain. The people who designed those applications are now sitting in jail. So let's talk about this topic that's so dangerous. Math. Cryptography. It's so dangerous. The reason why it's dangerous is because it subverts the power of Western governments. That's why it's so dangerous. And so let's talk about it. Let's friggin' make a whole video. We're listening to some house music. We're going to be vibing. So what are we doing today? I have two goals for this video. I want to talk about how we can prove the knowledge of a hash preimage of a hash function. And I probably won't have time, but I would like to explain the process of proving a hash preimage of a leaf in an intermediate Merkle tree. So before we begin, if you don't understand at all what I just said, I'm going to explain it right now. So what is a hash function? A hash function is a type of function that allows you to generate unique digests for given inputs. So for example, you have this string, the red fox jumps over the blue dog. You run that through your hash function and you get this output. Well, if you change one thing of that hash function, the red fox jumps over the blue dog, one letter was changed, you get a completely different output, okay? In this video, we're gonna be talking about, I'm gonna show you how you can build a zero-knowledge circuit that allows you to prove that you know some input for a given digest without revealing the input itself. That might sound a little bit crazy. And the reason is because it is pretty crazy, because zero-knowledge cryptography is genuinely magic. It's like black magic. And I like the quote by Elon Musk, any sufficiently advanced technology is indistinguishable from magic. And well, zero-knowledge cryptography definitely fits that description. So what's cool about zero-knowledge cryptography is, if you don't stick for this entire video, one last thing you should listen to, one point here that I'm going to make, is that zero-knowledge cryptography is going to be used in so many applications in the future. Right now, people are working on zero-knowledge virtual machines. That means any computation that's done in that virtual machine will generate an output, a proof, that allows other people to prove that that certain computation that was computed inside of that virtual machine was computed correctly for a given set of inputs. And those inputs can be public, anyone can know those inputs, or those inputs can be private. That's what's so cool. These things zero-knowledge virtual machines, they exist right now. They're just not very efficient, but they're going to get increasingly more efficient in the future. All right, so let's jump right in. Oh yeah, one last thing. I want to talk about the last goal that I have for this video is to talk about proving the knowledge of a hash preimage of a leaf in an intermediate Merkle tree. So intermediate Merkle tree, what is that? Merkle trees are used everywhere in computer science, but really heavily used in blockchain technologies. So it's essentially this. So you have to build upon the concept that I just described of the hash. So you have some hash function that hashes some input, and you have a set of inputs, essentially, or things, items in this set. And so you hash the first item, the second item, you get their unique hashes. Then you hash those two hashes. Then you do it with the other node, those two hashes, you hash them, and then you hash the tree all the way up to the root, and you get the Merkle root. And what's cool about Merkle trees is that if you change anything at all in any of these leaves, ever so slightly, the Merkle root will change. That's what's cool about Merkle trees. So the guys who are sitting in jail right now for building technologies based on ZK, using Merkle trees in a ZK context, they're sitting in jail. And all they did was they allowed people to use an application where they deposit assets into that application. And they can withdraw those assets if they can prove that they know the hash preimage of a leaf in this Merkle tree. That's all they did. And now they're sitting in jail. Pretty wild. Pretty wild. All right, so what I'm going to be doing is I'm going to be showing you how to get started building technologies that, I'm not saying I want you guys to go to jail, but I'm just saying just be careful when you're writing these things, because people who wrote these types of applications are in jail. Well, let's get started. We're vibing to the house music. Don't you like it? All right, so git clone ZK IMT, ZK intermediate Merkle tree. All right. All right, so I got to clean this up a little bit. So let's do IMT. And let's move this and the Nargo toml file under there. All right, so hash preimage Nargo init. So Nargo is the package manager, sort of like a package manager. It's like Cargo for Rust, but Nargo is for Noir. And Noir is this language. It's a open source domain specific language for safe and seamless construction of privacy preserving zero knowledge programs requiring no previous knowledge on the underlying mathematics or cryptography. That's what Noir is. So let's get started. All right, so we got to build this program where we know where we can prove for a given digest, a given hash, we know the input. We can prove the input without revealing the input itself. All right, so we have this. All right, so we're going to be using the Poseidon hash. So there are different hash functions for different. Oh my God, this is one of those ads. You probably can understand where my VPN is speaking Dutch. All right. Focus. All right, so hash preimage. I got my cheat sheet here. All right, so what I was saying, we're talking about hash functions. So certain hash functions people don't use for certain reasons. And the reason why is, okay, so for example, you would not want to use SHA-256 in a ZK context because it is inefficient. Because there's certain operations at the low level that are not efficient in a ZK context. So it's just more expensive from a computational standpoint. So that's why you wouldn't use SHA-256. Instead, there are different hash functions that are specifically designed for ZK contexts. Blake 3, Poseidon. I think there's Poseidon 2, 1, 2, 3. I don't know how many Poseidon versions there are. Then there's Rescue Prime Optimized. So there's a ton of different hash functions for ZK. But what's interesting is once you start going down the rabbit hole of ZK stuff, you realize that certain people in the ZK space don't use certain hash functions because the people who created those hash functions, they don't get along with them. So it's like this politics. It's like politics everywhere. Well, politics also exist in the realm of cryptography. All right. I gotta focus. It's hard explaining and coding. All right, so we got our hash. which is going to be a public field. And then we have our hash preimage, which is going to be a private field. So what we got to do is we have to we're going to hash our hash preimage and check that the hash preimage that we hashed inside the circuit is equal to the hash that the user inputs or provides in the input of the circuit. All right, so we're going to do internal hash is equal to Poseidon. I think it's BN254 hash 1 hash preimage. And what we're going to do, we're going to have a constraint where our internal hash must be equal to our hash. And if this passes, that means that someone knows a hash digest. They know a hash preimage for a given digest. All right, so now let's write our test. All right, so we got to do the same exact thing here. We got to do, okay, let our hash preimage, we're just going to let that be 0 for simplicity. Then we're going to let our hash equal Poseidon BN254 Poseidon. Oh, what am I doing? Hash 1 hash preimage. Boom. Then we're going to pass that into our main hash and hash preimage. This is a very, very simple test just to show that it even works. That's the whole point of this test. This is not a very good test. See, it passed. Look at that. Test is passing. All right, so now this is where the docs are so terrible. Noir docs. Noir developers, if you're watching this video, you're probably not watching this video, but if you are watching this video, the docs are terrible. And I've told you this in the Discord, and nothing was resolved. Okay, so what we got to do, all right, so we got to do, I think it's like Nargo check. All right, we got our prover. All right, so we got our hash, which we have no idea what that is. Our hash preimage is 0. And, oh yeah, so what we got to do, okay, yeah, I remember. Okay, so what we got to do, let's compute the hash, the Poseidon hash for 0 in Solidity. So let's go to Poseidon hash Solidity. I didn't spell that right, but it's still going to come up. All right, contracts. We're hashing one element, therefore we need this. Now we're going to paste this in here. Compiled, excellent, deploy. We have an array of uints. It's going to be 0. We hash that. Excellent. This is a uint 256. So we have to convert this uint 256 into a hexadecimal. So we got to go to hex. See, it's like the first thing that comes up because I do this all the time. Decimal to hex. Decimal to hex. All right, yeah, so see, I actually already did this one time just to check before the video. So yeah, this is our hexadecimal number. We have to prepend OX. Nargo execute. All right, so that created our witness. Cool. Now, I had to make a specific note of this part in the docs because I couldn't find it. So we ran Nargo execute witness name, just called it witness. Now we have proving backend. We got to run all this. All right, so bb prove target hash preimage.json target witness. Oh. Nice. All right, we generated this proof. Next, what we got to do is we have to convert this proof into a hex format. And ChatGPT really helped me with this. I'm not going to lie. And all right, so we got to go. All right, we got to create hash No. It's going to be called proof convert. Proof convert. Cargo init. Nice. All right, so what this script does is it converts that proof thing that I just made and it outputs it into a hexadecimal format. All right, I have to add hex dependencies to my cargo toml file. Great. All right, so this file that I have here, this main rs, it is reading proof from the directory. So let's just move proof into here. Cargo run. Didn't move it into there correctly. Okay. Boom! Look at that. There we go. Now what we got to do? We got to generate our solidity verifier with this. All right, so let's do this. Sorry, I got to go back. Hash preimage. Vibe to the house music. ZK and house music. I'm telling you, it's a great pair. All right, so Nargo, compile, BB, write, VK, B, target, hash preimage JSON. Boom, BB contract. Now we generated this thing, which is a solidity file. We're going to go into Remix. Remix is an online solidity development tool thing. Really good tool. All right, so this is my verifier, massive file. Look at all that math going on in there. All right, we're gonna deploy it. We gotta deploy not this, but the ultra verifier, deploy, boom. Look at that. Okay, so what we gotta do now? All right, so this is the whole point. This is the whole point that I'm trying to do in this video. Where did my hash, cryptographic hash thing go? Okay, what we did, we created a proof. This is our proof that we know that we have this hash right here. And the hash preimage is just 0. And here's our proof. This is what we're gonna do. So we copy this proof. We're gonna copy this proof. Boom, we copied the proof. We paste the proof right into there. All I did, pasted the proof. Boom, paste. Next, so this is a bytes 32 array. And our input is this hash. Okay, so paste that and look. Okay, look. This is equal to this public input, because my circuit right here, look at this, the hash is a public field. The hash preimage, we don't tell anyone about that. So this is an on-chain smart contract, and it's going to prove, it's going to 100% prove that we know the hash preimage of that. So this is a moment of truth. Let's check. True. It's true. So let's change one little thing. So from 93 to 92. And look at that, it failed. It failed. But if we do 93, it's good. It worked. It worked. So that's how you can prove knowledge of a hash preimage in a zero knowledge context. So I don't have time to go and do the entire intermediate Merkle tree type of thing, but I'm just going to run through the code and kind of explain it. All right, so intermediate Merkle tree, let's pull up the image. Vibe to some house music here. All right, let's just run through the code here. Hash, preimage, IMT, boom. All right, what's going on in this code here? And this is the same exact things that I just explained for the proving knowledge of the hash preimage. It's gonna apply exactly to this. So what I can do I can theoretically create a smart contract where people deposit assets to that smart contract, but when they deposit assets to that smart contract, they push a leaf to the Merkle tree that's stored in that smart contract. And every time they do a deposit, they push a leaf to the Merkle tree that's in the smart contract, and that root is changed because they added a new leaf. Make sense? Good. Makes sense to me. Okay, next. So what happens is we have this main function, which is just our circuit. We have the root, which is just the root of the Merkle tree. We have a nullifier hash, which essentially is, we're going to store the nullifier hash in the smart contract so that people can't just come along to our smart contract multiple times and start withdrawing assets from it, because that would be bad. We don't want that. So our nullifier hash is public. Anyone, when we're proving our circuit or doing our computation, we're proving it, everyone sees the nullifier hash. We also have a nullifier. Nullifier is just the hash. We're just hashing the nullifier. And we're checking right here. See this assert? Nullifier, nullifier hash. Nullifier hash must equal the hash of the nullifier. Makes sense. So the leaf that we're adding here is the nullifier. We're hashing the nullifier. We're hashing some secret number, which is private field. Nullifier is private field. Secret's a private field. Proof siblings. Okay, what is proof siblings? Proof siblings are the hashes of these individual nodes. So when you are proving that you know the hash preimage of a leaf in an intermediate Merkle tree, what you're going to do is you're going to be going, I don't remember if you hash from the top or you hash from the bottom. You're probably hashing from the leaf. You're probably hashing, yeah, you're hashing here. Yes, you're hashing from the leaf. So what happens is, we computed the hash of this leaf, which is just the nullifier and the secret. Makes sense, right? So we're just hashing nullifier and the secret, and let's just say that's this H1 node. Okay? Then, right here, let this mutable variable hash equal the leaf. Okay. And then what we're going to do, we're going to go through a loop 32 times. And all this means is, this is a Merkle tree with a depth of depth of 3. But theoretically, you could imagine a Merkle tree that has 32 levels. So a really big Merkle tree. And a Merkle tree with a depth of 32, I think, no. 2 to the power of 32, that's how many leaves it has. So a lot of leaves. Right now, this tree has 1, 2, 3. This only has 8 leaves. But imagine a Merkle tree with a depth of 32. It would have a lot of leaves. And you could have a Merkle tree with a depth of 64. And that's a big ass number right there. So a lot of leaves. And all this is doing is this loop right here. For each level, we're just doing the loop. So our proof siblings, they're all initialized to 0 in our test, just in our test here. And the reason why is because it's an intermediate Merkle tree, and I think that means that everything's initialized to 0. I could be slightly wrong about that, but that's what I think it is. And the proof path indices is, so if you want to select this leftmost node, H1, you would go 0, 0, 0, 0. But if you wanted H2, it would be 1, 0, 0, 0. If it was H3, it'd be, I think it'd be 1. Actually, I don't know. But anyways, the proof path indices will tell you which way to go. Like left, right, left, right, left, right. So that's what we're doing here. And in this for loop, see, we're switching things up here. We have a hash here. It's the left one. Proof siblings, right. If proof path indices is 0, then it's going to be hash, then proof siblings. But if it's the other way around, if proof path indices is 1, then it's going to be proof siblings left, hash right. And then we just prove, so then we're going to assert, we're going to do another assert that the hash that we supplied, or no, that we generated inside the circuit is equal to the root that we supplied here. That's all that's happening. That's all that's happening. So if we run this test, I already know this test is going to work. This is a very basic test. But theoretically, we could do the same exact thing in Solidity. See where I'm going with this? Exactly. So, this video might seem abstract, might seem pretty weird. I understand. That's the point of this video, is to be weird. That's the point. But it's also to show that I like zero-knowledge cryptography. And, I hope this video also piqued your interest towards zero-knowledge cryptography. All this code, let's just push this code right now, honestly. All right, we got an ad coming up. This is ridiculous. Let's vibe to some house music when I push my code to GitHub. So all the code in this video, it's all going to be public on my GitHub.
Who is this young lady next to you? She's one of my backup girls. Her name is Miss Madeline Strickland. Where are you from, Madeline? Chicago. How do you like it to be?
All right. We committed some stuff. We pushed it. All right. Thanks so much. If you like this video, leave it a like, maybe subscribe. Maybe go star this repository on GitHub. Check it out. Learn more about Noir. Noir is a great tool. I'm going to be building stuff with Noir in the future. I like Noir, and I like zero-knowledge cryptography. So if you like this video, let me know, and I'll see you the next time. See ya.